In a world of spells and potions rare, we seek the pairs beyond compare. When power joins with potions might, success is born in data's light. Welcome to Successful Pairs of Spells and Potions, where coding meets a bit of magic. In this problem, we are given two arrays. One represents the strength of spells and the other represents the power of potions. We are also given a success threshold, a magical limit that defines what counts as a successful combination. Our task is to find for each cell how many potions can form a successful pair, meaning that product is greater than or equal to the success value. Let's look at a first example. We have spells as 5, 1, 3 and potions as 1, 2, 3, 4, 5 with success equal to 7. For spell 5, we get 4 successful combinations. For spell 1, none of the potions work. For spell 3, 3 combinations succeed. So our final output is 4, 0, 3. Here's another example. Spells are 3, 1, 2, potions are 8, 5, 8 and success is 16. Spell 3 combines successfully with 2 potions. Spell 1 fails with all and spell 2 succeeds with 2. Therefore, our output is 2, 0, 2. From these examples, we can observe something interesting. The stronger the spell or the more powerful the potion, the higher the product. To succeed, a potion must have strength greater than or equal to success divided by the spell's power. That means for each cell, we just need to find how many potions meet that requirement. To solve this efficiently, we use sorting and binary search. First, we sort the potion array. Then, for each spell, we calculate the minimum potion strength needed for success. Using binary search, we find the first potion that meets or exceeds this strength. The number of successful pairs is simply the number of potions remaining after that point. This approach gives us a time complexity of big of n plus m log m, which is fast and scalable. Here's how the algorithm looks in pseudocode. We sort the potions. For each spell, we calculate the minimum required potion value by dividing success by the spell's power and rounding up. Then we use lower bound to find where that potion would fit in the sorted array. The result is the number of potions from that point onward. We store those counts and finally return them. Here's the C++ implementation of the solution. We sort the potions first, then iterate over each spell. We calculate the required potion strength using ceiling division. We use lower bound to find where it fits and store the number of successful pairs as the total potions minus that index. Finally, we return the result array containing the successful pairs counts for every spell. Let's trace this process with our first example. For spell 5, 1, 3 and success 7, spell 5 needs potions greater than or equal to 2, which is 4 successful pairs. Spell 1 needs potions greater than or equal to 7, hence 0 successful pairs. Spell 3 needs potions greater than or equal to 3, hence 3 successful pairs. The final output is 4, 0, 3, just as we expected. To summarize, sorting the potions allows us to apply binary search efficiently. The approach is both fast and elegant. It's a great example of combining mathematical reasoning with algorithmic thinking. This is a binary search problem disguised in a magical theme where logic truly becomes the spell. Every spell seeks its potion true, a perfect match in numbers too. Through logic's art, we find the pair, success awaits the ones we dare. And that's the beauty of algorithms, turning complexity into harmony and logic into a bit of magic. Thank you for your attention.